So in this video, we're going to look at some ways to take carboxylic acids and react them into different groups, and also a couple more ways to make carboxylic acid. Some things we've looked at, some things we haven't. So I'm going to start here by looking at the general reaction of carbonyl substitution reactions, which we've seen before, right, with these Grignard reactions, where we have things like esters and acid chlorides, right? So here we have our standard carbonyl. We react it with some sort of nucleophile, right? Break open our carbonyl to get to our tetrahedral intermediate. Our tetrahedral intermediate. And this step is the slow step in the reaction, where this happens the slowest. But the next step, going from our tetrahedral intermediate into something smaller, right, is a much quicker step. So this is our fast step in this reaction, and it's irreversible. Right, and our leaving group has left. And this reaction only really takes place when the L group there is a better leaving group than the nucleophile. And some things that affect this rate, making something go quicker, is things like, and I have the list down here below, things like sterics. So the more sterics that exist, the slower the reaction. Inductive effects, meaning electron withdrawing groups, increase the rate by making that carbonyl, right, more electrophilic. So anything that can make this carbonyl more electrophilic means the reaction is going to happen faster. And the last thing that affects this is resonance. So electron withdrawing increases the reaction rate, and anything that donates decreases the electron, decreases the reaction rate. So something like chlorine, right, as a leaving group is pulling pretty hard on those electrons, right, making that more reactive. But anything with resonance may also increase that reaction rate. And we'll look at some examples of this going forward. But kind of the trend you probably notice at this point is whenever there's kind of a question like this of what affects a rate, some sort of vague question, things like sterics or resonance tends to be the answer, right? All right, so let's take a look at this chart here that I've provided. And this chart is just a general reactivity chart. So in terms of reacting with a carbonyl like this, right, we get more reactive going up this chart here. So acid chlorides or acyl chlorides, right, are more reactive than, looking down below here, any of these bottom compounds, right? And it has to do with that kind of those couple of reactivity guidelines I mentioned in the last slide. And so this is just a general chart here, just for kind of your FYI. But in general, right, you can kind of see the trend happening here, where something with a chlorine, right, makes us more reactive. This other group here, an anhydride, which is sort of this, it almost looks like a double ester, right? Do we see that? And the leaving groups, right, chlorine leaving group, this sort of conjugate base carboxylic acid leaving group has resonance, right, making this a good leaving group. And this has inductive effects, right, the chlorine, so that makes it a good leaving group. That's why these are at the top of the list. And so we've seen these sort of leaving group situations happen before with primarily, right, acid chlorides and then esters, right? But we can see acid chlorides are much more reactive than esters. And then for these middle two here, right, notice is not a leaving group. That's because these are addition reactions, right? There's no leaving group really present. So these are only additions. And what we'll see in the rest of this video is that there are ways we can make things like these acids and amides into better electrophiles. We can transform them into something like anhydrides or acyl chlorides to make them more reactive. And so I won't go over this sort of review here of synthesis of carboxylic acids. We did that in class, so I'll leave this up to you to sort of dig through on your own if you haven't already. And so some new ways that we can make carboxylic acids is with the cyano group, this nitrile group, right? Remembering that CN is this carbon triple bonded to a nitrogen. We've seen a few different reactions involved in them already, and there's two different ways we can transform them here. Notice we have kind of similar conditions above these arrows I've listed. The top one, these are harsh conditions, and below we have these mild conditions. And with the harsh conditions, what happens is we make a carboxylic acid, and with the milder conditions, notice there's no heat there, and we're not using sulfuric acid, which is notably harsher. We make an amide. I won't go over the mechanism for these. You can look at that on your own. But this is the sort of, these are two new reactions we can use to transform cyano groups into carboxylic acids and amides. For the next one here, saponification of esters, we've looked at that in great detail already, right, especially with our Alice Ball problem set, but I'll quickly sketch up the general reaction here, where we have some sort of base, NaOH, KOH, water, and then in the second step we have some sort of acid. We can use HCl or something like that too, where we're transforming, right, that OH minus, that hydroxide, is attacking our ester, right, in that substitution reaction to kick off that ether leaving group, right, and we get to our carboxylic acid afterwards. We can do something very similar with amides. So this is called an amide hydrolysis. And hydrolysis here, saponification of esters also has this terminology, hydrolysis or hydrolysis. Essentially, right, if you break this up into two words, it essentially means water, right, hydro, and then lysis means to cut. So we're using water to cut up this amide or amide. So it's very similar to our last reaction here. We have an amide of some sort. We actually do this in under acidic or basic conditions. And I'll put both conditions on here. So we can either use NaOH, water, right, these basic conditions, with a final quench to transform our amide into a carboxylic acid, right, using very similar mechanisms to the saponification of esters. So I'll leave that mechanism up to you. Or we can do acidic conditions, where we start with acid, right, HCl, or some sort of acid, doesn't matter what, followed by, right, and water here is important. And the second step, we quench the reaction to get to, again, our carboxylic acid species here. So those are some ways we can make carboxylic acid and amides. But let's go ahead and look at some reactions we can do with them. So the first thing we're going to look at is these acyl chlorides, right? That carbonyl, just to refresh our minds here, right? That carbonyl with a chlorine on it, acyl chloride, or acid chloride, they're sometimes called. So there's some ways we can make acid chlorides, right, where we have some sort of carboxylic acid, doesn't matter what, which is what this R group here is for, right? And then we can react it with something called, I'm going to redraw that. We can react with something called thionyl chloride, which is this interesting looking group here. And this, essentially all this does is it supplies the carboxylic acid with a chlorine to make our acyl chloride. And sometimes thionyl chloride is abbreviated as SOCl2, so you'll see it written like this pretty often. And this acyl chloride is really reactive, right? And so we can reverse this reaction by simply just adding water or to some sort of base, and that reaction will reverse really quickly to get back to the carboxylic acid. So in real life, right, when we're doing these reactions with thionyl chloride, this particular acyl chloride here is really reactive. So we tend to make sure things are really dry because it will go back to the carboxylic acid, which, right, isn't great when you're trying to do chemistry. So, with acid chlorides and other groups, we can make anhydrides, right? And to remind ourselves, right, anhydrides from that list I gave earlier is this sort of functionality here. With this sort of almost double ester looking thing, right? Two carbonyls flanking that oxygen. And anhydrides, right, if you remember, are pretty reactive too, right? They're almost as reactive as acyl chlorides. And so some general reactions we can do here involve, for this first one, an acyl chloride and a carboxylic acid. And we use something called pyridine, which is a base. And it is this molecule that may look a little familiar from our aromatic chapter. So this is pyridine, right? And that nitrogen, as we discussed with its lone pair, that lone pair is ready to act as a base because it's not involved in resonance, right? So pyridines are a really good, they're a really good base and a terrible nucleophile, primarily because it's so big. But it's happy to act as a base. So what this does, right, effectively is the pyridine is deprotonating the carboxylic acid to make it a good nucleophile. So that's all that's happening here. The pyridine is reacting with our OH here to make it into O- and make it a good nucleophile. And so the reaction, right, as you can imagine, right, again, our chlorine is our leaving group, oxygen is our nucleophile, and then our carbonyl carbon here is our electrophile. So we get this anhydride as our final product here. And I'll leave the mechanism up to you, but we can certainly look at some mechanisms involving these in class. Right. And we can also make anhydrides with anhydrides. So with this acetic anhydride here, and again our carboxylic acid and our base, right, to deprotonate our carboxylic acid to make it a good nucleophile, we have our nucleophile, and then our leaving group is going to be this whole unit here. So this whole thing is going to be our leaving group, and then, right, our carbon here, our electrophile. Right, and so when we bring these all together, we get this quote-unquote mixed anhydride, which is just a fancy way to say that we have an anhydride that is asymmetric, right? They have different groups on either side. Right, and then we don't have to show it, but the leaving group for this, right, is this carboxylate group down here, right? This is our leaving group, right? So it's important to kind of keep in our minds what groups are kind of coming together here when we're splicing together these groups. We can also do something very similar with esters, right? Very similar reaction, right? We have our acyl chloride. This time we have an alcohol instead of a carboxylic acid. But our pyridine, right, our base is doing the same thing. It's making our alcohol into an O-, right, which makes it a much better nucleophile. Right, and so with all that in mind, right, this reacts with our acyl chloride here, and we get to our ester. Another type of reaction we can do is something called the Fischer esterification, and this is done under acidic conditions. We saw something similar to this in the Alice Ball problem set 2, where we had started with the carboxylic acid, and we used acid in order to attach an ester group to it. So we'll take a look at what this looks like and what's happening. So we have some sort of general carboxylic acid here, and we have some sort of base, so we'll just do, actually I'll draw out the full thing. We have ethanol, right, a carboxylic acid and alcohol, and we include an acid. We get to, right, the resulting ester. What's happening here is the acid, right, is transforming this into something more electrophilic. Right, because that carbonyl is going to be taking that proton, making the carbonyl more electrophilic, and then at the same time, the OH will become a better leaving group by protonating it. Again, with the acid that's present. So the acid is essentially making the carbonyl more electrophilic and the OH group a better leaving group. All right, so for this last bit here, we're going to look at making some amides. So, looking at this first reaction here, this carboxylic acid, something we can do with it is look at, well, first we're going to break this up into 2 different steps here, right? One, we have this SOCl2, remember this is thionyl chloride, right? And in this first step, essentially what's happening is we're making, with chemistry we've already discussed, making the acyl chloride, or the acid chloride, right? So now it's a much better, we have a much better electrophile now, right? Because carboxylic acid is a poor reactor, but an acyl chloride, right, is much better, right? It has a much better leaving group present. So we're making the species more reactive. And in the second step, right, we're doing this amine substitution, where the amine is going to come in and kick out that chlorine leaving group. And so our product here in this case is this, where that amine, right, has come in and kicked out the chlorine to get to our amide. And with our second bit here, the amine is going to come in and react right away with our, right, remember this is our anhydride here. And so our amine is going to come in, right, our nucleophile. We have our leaving group here, right, that whole thing is a leaving group, right, it can do resonance. And then we have, again, our electrophile. So our final product in this case, our amide product, is once again this, right? And throughout these reactions we've been looking at, essentially what we've been doing is looking at ways to, right, make carboxylic acid, sure, but also how to react them, especially with this first example here. We can figure out ways to react them to make them more reactive than they otherwise would be, and then we can do more chemistry with them. We can take these carboxylic acids, make them into more reactive species, and then do further reactions with them. And this is really important chemistry for things we'll kind of look at down the road. But hopefully, right, I know these were a lot of reactions, we're kind of looking at a lot of new chemistry here, but hopefully, you know, through pattern recognition and sort of getting more used to chemistry in general, doing these organic chemistry reactions, hopefully all this is making a little bit of intuitive sense, and we'll certainly look at more of these reactions in class as well to get more practice with them.